Hello, this video is to go over inertial versus non-inertial frames. This is a topic that we didn't get to in class today. Um, so the main idea is written right here. As a reminder, Newton's laws, in particular, the net force equaling mass times acceleration, that's only valid in an inertial reference frame. So an inertial reference frame is one that is not accelerating. So this is a frame where there's no acceleration, zero acceleration. The frame itself is not accelerating. So an example is you at rest on the Earth. I mean, really, there is a small acceleration because of the rotation of the Earth, but it's negligible. So it's basically you're at rest. You're not feeling like you're accelerating very much. But if you're like in a plane that's taking off, that feels like you kind of feel pinned against the seat or something, right? That's a non-inertial frame. So rather than a plane, we have a train here to also emphasize this point. So imagine this train is accelerating quite. So it's not just moving fast, but it's changing speed. It doesn't matter if the train's velocity were constant, it would actually be an inertial frame. So it's important that it's accelerating. Um, so the acceleration is to the right for this train. As long as you're in a reference frame outside of the train, then you can analyze anything that's going on inside the train. So for example, you have a ball that's hanging inside the train. And because of the acceleration of the train, that's going to affect the way that the ball just kind of hangs there. So the ball kind of goes back a little bit, right? Relative to it was hanging right here, but it's no longer hanging there when the train accelerates. Right? It swings back a little bit. Why does it swing back? The reason is that the net force, in order for the ball to move with the train, there has to be a net force in the direction of the acceleration. So if you look at this free body diagram, you'll notice the net force, the sum of the two forces acting on the ball, the tension and the gravitational force, this is to the right. So the only gravity, mg, cannot accelerate this ball to the right. Right? The ball tied to the string, tied to the train, forces the ball to move along with the train. So the only way to get a horizontal force on the ball from this situation is not going to come from gravity. It's got to come from the tension in the string. And the tension can pull up and to the right as long as the ball swings back like this. So the train starts accelerating, the ball starts its swinging back as the tension for the horizontal component of tension needs to get bigger and bigger to have the acceleration get bigger and bigger to become the acceleration of the train. So this is Newton's laws are true. So Newton's laws are true. This is true. We're in an inertial frame. Everything is working out just fine. The problem starts to be if you look at a non-inertial frame. So what does this mean? Imagine you're standing inside the train. Okay, so this person is the non-inertial observer. Okay. So what the non-inertial observer is going to see, so I'm going to cross this out for a second. What the non-inertial observer sees is that there's a tension force and an mg acting on the ball. Okay, that's going to be the same as what we just analyzed. Okay, so suppose like instead of a string, it was some spring, and you can measure exactly how hard the spring is pulling on the ball and how big mg is. You already know the weight of the ball. Okay, so those two are unaffected. But the non-inertial observer is going to say that the ball is at rest in their frame. Okay, so this person says the ball is at rest, even though the net force is non-zero, even though the sum of the forces is not equal to zero. So Newton's first law is not true, according to this non-inertial observer. And that's right, Newton's first law is not true. There's a net force, but the ball's at rest. And so are Newton's laws garbage? Well, you have to keep in mind that this is only true, these laws are only true in an inertial frame. You have a non-inertial observer, or a non-inertial frame, same thing. These Newton's laws are not true. That is, unless you introduce what are called fictitious forces. So if I go back and I say, okay, so if we kind of invent a fictitious force Then you could say, well, the ball's at rest and there's some fictitious force that's pushing it back, and now the net force is zero and the ball's not accelerating. So Newton's laws become true, but you have to introduce this fictitious force. Okay, so I'm going to cross it out because we don't like introducing just things that are fake, right? And that's exactly what's going on with the centrifugal force. So what's going on here, so we're going to look at this picture first. If you are on a merry-go-round, so you're all of a sudden in a non-inertial frame because you are accelerating in the circle. So what happens here is that imagine all of a sudden like that we could there was absolutely no friction. So there's mg in the normal force, okay, acting on this thing. But imagine we were able to turn off friction totally. What you would say in that inertial frame, so all of a sudden what would happen if there was no friction and nothing pinning something to the merry-go-round, what would happen is that object would start to slide radially outwards. Okay, so there is what's called a fictitious force in this frame. Okay, if so something will affect the motion of the object. So that an object is not going to remain at rest on the circle if you only have n and mg. There's going to be a force that's radially outwards, and we call that the centrifugal force. Okay, but this is a very like kind of made up weird thing. This is only so let me emphasize this. This is a made up thing because of the weird reference frame. Because of the non-inertial frame. And this is why, so centrifugal force is a thing, and you can define how big it is, and you're aware of it. You know, if you're moving in a circle, it feels like you're being pinned back, something, right? When we were talking about the example of Bob the Block at the amusement park ride where it's spinning forward, it really feels like you're being thrown back against the wall. Okay, this is the centrifugal force because you're in the non-inertial frame. But it's a made-up fake thing, is the point here. What's better is that if you're in an inertial frame, so if you're someone who's standing outside of the merry-go-round, you recognize that there are no such things as these fake forces. You have mg and you have a normal force, and the only way for this horse thing to keep moving in the circle is for there to be an actual inwards force keeping it moving in a circle. Okay, so there has to be some sort of, I'll call it F, there's some real force pushing it inwards to keep it moving in a circle. The way you would describe this over here, so something's moving in the circle in your non-inertial frame, you're going to have that F real force that's going inwards and the centrifugal force that's going outwards. So here the net force is zero, and that's why the object's at rest in the inertial frame. Okay, so in the non-inertial frame, something moving in the circle, something looks at rest in the non-inertial frame, and the net force is zero in that non-inertial frame. But the better way of looking at it, the way we're going to emphasize in this class, is we're going to use an inertial frame. We only look at real forces. Notice how there's no fake force here. There's only three forces acting on this thing. And it's this real force, whether it's friction or maybe something, maybe it's the person holding on to the pole on the merry-go-round to keep them from flying off or something. There's some real force that's keeping the thing accelerating to move in the circle. So as a reminder, Newton's laws are only valid in inertial reference frames. To avoid any confusion, use inertial reference frames. No such thing as centrifugal forces. Okay. An object in uniform circular motion requires a net force radially inwards equal to mv squared over r. And the radially inward acceleration is called the centrifugal acceleration. Okay.